Okay. So in the previous lecture, where we end up finishing is the creation of the thread, right? So we are looking at how to create the multi-threaded application and what is the difference between the multi-threaded application and multi-process application. So we looked at that difference, and now we are in the process of creating the threads in our application. So you have the application and you have the main thread. So you can basically any process that we are running, right? So if you look at this picture, any process that we are running also has a default thread. So whenever you write your main function, it has a process ID as well as it has the thread ID, right? So this is the simple threading environment. And then you can actually have a single process create multiple threads also, right? So one process can create multiple threads within them, and each of the thread will start from a different function or the same function. So you can create multiple threads within the application where we can start the function. Now, the passing of the parameter to those functions is not very trivial, because the specific signature of the thread function is that you have to always use void pointer for the return type and the void pointer for the argument, right? And so what we said is that when you create when you create a thread, this fourth parameter is something where you can actually pass the argument to the thread function. And so we had looked at three of the scenarios where you don't want to pass any parameter, you want to pass a single parameter, or you want to pass the multiple parameters. So how each of these things can be done, right? So that is what we looked at till now. Now, the one of the issue that we see when we create a multi-threaded environment, see, if you have multi-process environment, in the multi-process environment, we said that even if the parent process terminates before the child process, right, the parent process will terminate, but then the child process will be allowed to continue to execute. Why? Because the child process is adopted or inherited by the init process, and the init process will become the parent of the child process. Now, in case of the threading environment, because all the threads belong to the same process, right? As you know, you can see this example in this picture, right? So this is a single process, right? This whole thing is a single process, and each of these threads belong to the same process ID. So there is no such thing as a parent process and the child process in this case, right? But a single process does have multiple threads, and therefore what happens is that if the process terminates, right? If this process terminates, then all the threads that are running within that process will also terminate. Okay, so if you write an exit command in any of the thread, which basically terminates the process, then all the threads will terminate. Okay, so we cannot really write exit, because if you write exit, meaning that you terminate the process, and then all the threads that are running within the process will terminate. Okay, so we cannot really write exit. Also, in your main function, let's say if we are creating the return, if we are creating a function, main function, and we put the return, right? So you can basically exit the code using exit, or you can write a return in your main function, right? So if you write this, the process will end. If you write this, the main thread will end, and whenever the main thread ends, all the child thread created within that main thread will also end. Okay, so what we will do is that we will take a look at an example of each one of these, right? How does exit work? How does return work? And then there is a special system call that is provided to us by the operating system. So the pthread exit is a special exit system call that allows only the current thread to exit. but any of the child thread created within that thread will not terminate. So we want to ensure that when a single process has multiple threads, right, and one of the thread terminates, then not all the other thread must terminate. Okay, so if you want to do that, then pthread exit is the system call that you need to use at the threading function. Okay, so we'll take a look at example of each one of them. So let us first start with the exit command, right? So in this case, if you see, we have the main thread, which is the number that will be displayed here. Then we are creating the child thread. Okay, we are creating the child thread. In the child thread, we are going to be executing this function. Okay, and this is where this operating system will be returning us the thread ID which we are creating, right? So if you recall, I mentioned this in the last lecture that within the child thread, if you want to know the thread ID, you can always use pthread self, which is same as get PID, right, for the threading function. And in the parent thread, it is the operating system is going to return the TID. So similar to the fork, right? In the fork, the parent process will get the PID of the child process. Similar to that, in the parent thread, whenever you issue the pthread create system call, then the thread ID will be returned by the operating system. So the parent thread will know what is the thread ID of the new thread, new child thread that is created. Now what we do is that we sleep for some time, okay, and actually let me just comment this line out. So we sleep for 1 second in the main thread, and then, you know, while we are sleeping, so that the child thread actually begins running, and then the child thread is going to execute just these two printfs, and then it is going to call exit. Okay, so as I mentioned, exit is the system call that you can use to terminate the process, right? Not the thread, but the process. What does it mean? It means that the main thread is in the sleep mode and the child thread is executing the exit command, which means that the whole process will terminate. So this process has two threads. One is the main thread and the other one is the child thread that is created using the pthread function, pthread create function. So we have two threads in a single process. But when the child thread is going to execute the exit command, then the whole process will terminate. And so what will happen is that if you look at it, this printf statement will not get executed at all. Because while the main thread was sleeping, the child thread exited using the exit command, which is basically terminating the whole process. And when you terminate the whole process, all of the threads within that process will be terminated. Okay, so we will see that this printf does not get executed in this particular example. Okay, so let me just compile this code again and run it. So GCC minus pthread thread example 1 dot c minus o thread example 1 dot out. Okay, I double dot, and then thread example 1 dot out. Okay, so now if you see, if I run n number of times, it doesn't matter how many times do I run, right? But you will see that, you know, the main thread is starting, right, which is the message coming from here, and then the child thread is starting and child thread is exiting, right? So those two messages we get, right? Child thread is starting and child thread is exiting, but then we never get this particular message, the main thread finishing. This message we are not getting. Why? Because the child thread is executing exit command, which is going to terminate the process, and therefore the child thread as well as the main thread will be terminated. So there is no way that the main thread is executing these two sentences, right? These two statements. So this is what happens with the exit. And now let me put a higher sleep for the child thread and lower sleep for or lower number of seconds, right? So 1 second for main thread and 2 seconds for the child thread. Now what will happen is that the main thread will terminate because the 1 second sleep will be over. So it will display this message and then that will execute the exit command. But the child thread is still in the sleep mode. So now the child thread will not be allowed to execute these two lines. Okay, so that is the example we will see also. Just to confirm, just to make sure that you understand that this is how it works. Okay, so you see that now, no matter how many times I run that, the child thread will start, but child thread will never finish because the main thread is finishing before the child thread and it is calling an exit function. So the child thread is also terminating because the process is terminated. Okay, so this is how the exit command will work. Right, so as we say, exit means process ends. Now when we look at the return, right, so in the second example we are looking at the return statement. So we can call the return statement from any of the function, including the main function, right, or even the child thread function. So whenever you call the return, the functionality, the way it will work is that the parent and all the child thread will end. So let's say if you write a return statement in the main thread, then the main thread and all the child thread that are created within that thread will be terminated. Okay, if the main thread does not execute return but the child thread is executing return, then that child thread and the child of that thread will be, so the grandchild thread will be terminated. So we have an example like that here. So what we have done is that we have the main thread. Right now the main thread is creating a single thread here, right? But now if you look at this particular function, the thread function, it is creating one more child thread. So this is the child thread of the main thread, and then this is the child thread function for the child thread. So we are calling that as a child thread, right? Grandchild thread. Right, so that is what we can also do. Similar to, we can do the same kind of thing in the process management also, you know that, right? So you can have a parent process creating the child process, and then that child process can also run another fork to create one more child process. So same thing we can do in the threading environment also. So the main thread is creating a child thread, and then the child thread is creating one more child thread of its own, right? And we have a sleep for 0.25 seconds here in the child thread as well as the child thread, and then in the main function we have the sleep for 0.5 seconds. Okay, why we have 0.5 seconds? So that we make sure that at least this child thread is created, generally speaking. But again, depending on when the operating system is starting to create this child thread and starting to create this child thread, maybe this thread will be created and maybe this thread will be created, but sometimes only this thread is created and this one may not be created. So it depends on when the operating system scheduler is starting to create the thread and allocate the core, right, for execution of a function for a respective child process. Okay, so what we are doing is we are doing the return here. So what does this mean? It means that if the main thread is finished first and it executes the return, right, then all the child thread from that main thread will be terminated, meaning this thread will be terminated as well as this thread will be terminated, and it may not even allowed to run. If the thread is not really created, then it may not even execute. But if this main thread is taking time to run, and if the child thread and the child thread is created, and if the child thread is executing this return, then this thread will terminate and this thread will terminate. So these two threads will terminate if this return statement is executed. That is what I am trying to show you here. Okay, so the return statement allows you to basically it terminates the current thread and all the child thread that are created from within that. So again, when we execute this code, you will notice that each time we get hopefully different answers or different output depending on which thread is allowed to start and which thread is allowed to terminate, right? So each time you will see that there will be a different output, hopefully. Right, so each time there is a different output, right? And depending on whether the return statement is executed before the printf or after the printf, depending on that, these messages will come. Okay, that is what I'm trying to say. So in this case, let's say the main thread finished, and then immediately after that, the return statement was executed. So the child thread just started, but then the return statement executed. So nothing after that got executed. But in this case, the return statement did not execute until all of these messages were printed. So return statement would have executed here, and therefore the child thread actually continued to run even after displaying this message. Okay, so what I'm trying to say is just you have to remember that when you write a return statement, it will terminate all the current thread, the current thread and all the child thread that is created from within that. Now, we don't want this to happen. We don't want the child threads to terminate, or we don't want all the threads that are created within the process to terminate when one of the thread wants to exit. Let's say the main thread wants to exit, but we want the child threads to continue, right? What can we do about that? So what we will do is, instead of using a return statement or an exit statement in our function, in our main function, we can actually call pthread exit function. So pthread exit function is a special system call that is provided to us by the operating system that will allow the current thread to terminate or exit, but all the child thread to continue to run. Okay, and that is that is the system call that we can use then to have all the child thread continue. So that is our third example here, right? So in this example, what we are doing, we have the child thread created, which is calling the thread function, right? And in this function, we have put 1 second delay purposefully so that the child thread will always terminate after the main thread terminates. So main thread is terminating after 0.25 seconds of delay, whereas the child thread is waiting for 1 second. So therefore, the main thread will always terminate before the child thread. And in the child thread, in the main thread, we have put here pthread exit, right? So we have not put exit or return, but we have put pthread exit. What does that mean? It means that the main thread is allowed to terminate, but without having the child thread terminate. So child thread will be allowed to continue to run because the main thread is exiting using the pthread exit. Now, if you don't put anything here, by default, the main function will actually execute return statement. Okay, so also you have to remember this, that if you don't put anything in as a last statement, whether exit, return, or pthread exit, the default is going to be return statement. So it is going to act like the return statement. So you have to make sure that when you have the threaded application, you make sure that your function actually has the pthread exit call and not, you are not skipping any of the calls. If you skip calling any of the exit command, then the default will be the return command. Okay, so this is what we want to do. So pthread exit will be executed here, and then the child thread will be continuing to run. It will terminate after 1 second after printing this message, and then it will call the exit command so that the whole process will terminate. So this is how your third example would work, which is basically to showcase that how we can use the pthread exit command. So you can see that there is a slight lag between the this message and this message. It is because of that 1 second wait, right? 1 second sleep for the child process. But every time you will notice that there is always this message coming, right? So the child process will always be allowed to continue and print this statement even if the main thread has completed, because we are calling the p thread exit in the main thread and not the return or the exit statement. So this is something that you need to keep in mind. Any questions till now, whatever we have covered?
Sir, how did we get the number 0.25 as just enough for that thread to finish?
I'm sorry, this number? You are saying
Yes,
how
sir.
did I come up with this number?
Yes, sir.
See, I didn't. Basic idea behind putting this sleep is so that the operating system gets a chance to create the thread, right? If I don't put any delay here, it may be possible that the main thread terminates as quickly as before the operating system even gets a chance to create the child thread. So just to make sure that the operating system has created the child thread before the main thread terminates, I put this sleep. That's all. So, I mean, it might work with even 0.1 second also. I mean, 0.25 is not a magic number. Does that
Okay,
answer your
sir.
question?
Because yes, sir. Sir, the question came because here it is just enough wait for the child. So, is it exactly the wait for the child thread to start?
Well, okay. So you are confused with the with the comment here, right?
Yes.
Yes. Please forgive me. Basically, this comment is just saying that I just want to put enough sleep in the main thread so that the child thread is created. So it's not actually enough. Let me just put just enough time, right? Or maybe we can just say wait for enough time to wait for enough time for the child thread to create it, child thread to start.
Yes, sir. I am getting it. Yes, sir.
Right. So basically, again, 0.25 is not a magic number. You can try it with 0.1 also. You can try it with 0.05 also. Depending on the speed of your computer and the scheduler of your operating system, it may start very quickly also. Right. So that's what I'm saying. Okay, now we come to the, we said that we can use pthread exit if the main thread wants to terminate before the child threads are terminating. But if you recall, in the process management environment, we had a way where we could say that the parent process will not terminate unless all the child processes are terminated. And we used to use a wait system call, right? So the wait system call allowed the parent process to wait for the child process to terminate. So similar functionality also is provided in the threading environment, and that function is called pthread join. The only difference is that in the wait system call, we could wait for any child, right? So we didn't have to always provide the child process ID for waiting. Whereas in case of pthread join, we do have to always provide the thread ID. So the main thread or the parent thread can provide the thread ID for which the thread the parent thread wants to wait for. Okay, and one additional functionality that the join provides us, see, in case of process management, there was an exit code that was coming back, and we were able to read that using that status variable that is returned back from the wait system call, right? So similarly, in the threading environment, we have the functions, right? So we have the function. So in the function, it could actually have the function could return the return value back to the main thread function. So the child thread function can actually return the value back to the main thread function. So the pthread join functionality even allows you to read that return value. And that return value, we can get it using the pthread exit. So pthread exit statement, if you see in our previous example, it did allow us to send the return code back. So we can use this functionality to return the value back to the parent thread. Okay, and that is what we are going to look at in the next example. So here in this code, what we are doing is we have the main thread, and then we are creating two child threads. Okay, so the ID is going to be TID1 and TID2, and then we have two different thread functions. You can actually use the same thread function also for two different threads if you want to, right? But in this example, we have used two different thread functions, THRFN1 and THRFN2. And in the THRFN1 and FN2, basically what we are doing is we are putting a sleep initially here so that the thread function takes time to run, right? Not that immediately it finishes. And then in the thread function 1, we are actually creating this global variable in the heap, and that value will be returned using the pointer. Okay, so we are creating the pointer variable, and then we are passing the pointer of that pointer variable. So it is actually double addressing. And if you look at the the second argument that we have in this pthread join function, it is pointer to pointer, right? So pointer to pointer. So you can declare a pointer of any specific data type, and then you return the address of that pointer variable to actually read the return value back. Okay, and so this is what we are doing here. Similarly, in the thread function 2, also we are putting sub sleep, and then we are returning the value 2. So the thread function 1 will return the return value 1, and in thread function 2 we are returning the return value of 2, right? Now in the main function, after creating both the threads, immediately after that it will actually do pthread join. Okay, so it will do pthread join for TID1 and TID2, and this is the variable which is again declared as the integer pointer variables. And these are the return values. These are the variable which will capture the return values that is coming back from this pthread exit command. So you can use either pthread exit or you can use the return also. Now, why we are allowed to do the return here? Because this is the innermost thread, and there is no child thread created within this thread. So even if you do return, it is not going to terminate any of the child threads, because this is the innermost thread. Right? If you look at the tree hierarchy for the threads, you know, your main is the main thread, and then you have these two as a child thread, and that's all we have, right? So even if you do return in this case, there is no harm, right? That is again something that you can keep an eye on, right? So we do pthread return, and we are waiting for the thread 1. And then this is the variable which is going to be void pointer. We are doing typecasting because that is what the signature of the pthread join says. And then we are going to be passing the address of this pointer variable. And so we are going to be getting the address of that pointer variable, and using that pointer variable, then we can actually print whatever is the return value we receive. Okay, so this is this is how we can actually get the return value back from the thread function. So we know that whenever you have a function, you have the argument that you can pass, and there is a return value that you can retrieve, right? So we have shown both the ways, both the things, how it can be done. Passing of the parameters also I have shown you earlier, and now using the pthread join, you can actually read the return value back. And that is the reason we have to use the pthread join, because that means until the thread function for that thread terminates, the main thread will not be allowed to terminate, because it needs to read the return value back. Okay, so similarly, we are also doing the same thing for the thread 2, right? So for the thread 2. Now, obviously, ideally, you want to put this command right after the thread creation. I agree, we can change that code. But in this example, it is also working because we have the 0.25 second delay in your thread 1. So by the time the second thread is created, the first thread is still not terminated. Okay, so it is working fine without any issue. So this is how you can actually use the pthread join to wait for the child thread and to read the return value back. So let's execute that code. Right, so you will see that the main thread started, and then there are two threads which are created, and then you have the main thread is now going to be using the pthread join. So it is going to be waiting for this thread. The thread 1 function is exiting. It is exited with the exit code 1, right? So this message is actually coming from the main thread. So if you look at, so this one, main thread will wait for child thread, and that is what the message we are getting from the main thread. And then once the child thread is exited, we get the exit code as, or the return code from here, right? And then similarly, we get the same thing for the child, second child thread, right? So now the main thread is, so here is again the pthread join is executed, and then now the second child is exiting. It has exited with the exit code 2, and now the main thread is exiting. So basically, these messages are coming from the main thread, right? And these messages are coming from the child thread. So this is how you can actually make sure that your main thread is not terminated until, or not exited until your child threads are terminated. Any questions? Okay. Now, see, in the process management environment, right, what was the shared data? Right. So when you have multiple processes, what information can be shared? So when you look at multiple processes, the only thing that is shared is if you have the same file open, right? If you have the same file open in two processes. So let's say you may have different file handles, okay? Or you may have the same file handles because you have done the fork after opening the file. We have seen this example, right, in the file IO case. So you can open the file in the main process, and then you create a fork, or then you do the fork which creates the child process. So the parent process has the same file handles or file descriptors, and the child process also has the same file descriptors, and you can actually share the same file descriptors in the parent and the child process. And we have seen that the race condition can happen with the files when you have multi-process environment. We saw an example with the standard output device, if you recall that example, right? So we tried to print one character at a time from the parent process and the child process, and we did see the race condition. So in the process management, or in the process multi-process environment, the race condition happens generally only with the files. Why? Because the data area, the global data area, is separate. It is not same. Even the local data area is separate. So the changes that you make here in the data is not available in this data area because they are two different data areas, two different addresses, right? But look at this environment, right? Look at the multi-threaded environment. In the multi-threaded environment, the global variables that you create are shared between all the threads. So any one thread making the change over here and any other thread trying to read or write the same variable in the global data area will have race condition. So in the multi-process environment, only the files generally have the race conditions, right? Whereas in the multi-threaded environment, the files could have a race condition as well as your global data can have a race condition. And files is, yes, a concern, but even more concern is with the global data area. Because what if one thread is trying to read the value while the other is updating the same value? Okay, and that is an example that I'm going to show you next, right? That how the race condition happens with the global variable in multi-threaded environment. So when you look at this example, we have two functions that are being called from two different threads. Okay, so thread 1 is calling the increment count variable, and the thread 2 is calling the print count variable. And count is nothing but this counter variable. So counter variable is my global variable, right? Because it is declared above all the functions. So this is my global variable. And if you look at the print count function, it is all it is doing printf. Right? So printf the counter variable for n number of times. And similarly, my increment count function is incrementing the counter value again n number of times. And it has, approximately the same number of sleep. Again, I put this sleep so that, it doesn't happen that the first thread started, it finished all of its operation, all of its iteration, and then the second thread starts. So I wanted to make sure that there is enough sleep in each of the thread so that the synchronization is happening, or actually both the threads are running in concurrent mode. That is the reason we have this sleep mode. Okay, I could have put the sleep here also at the top and not within the loop, but putting it in the loop actually makes it more sort of running it concurrently. So the idea here is that this thread is reading the counter variable and this thread is writing the counter variable, right? So you have read and write happening simultaneously for the same global variable, and therefore we believe that this code will create a race condition with the global variable count. Okay, and why would that be? Because if you run this code and see it for yourself, you will know. So you see that first time when I run, the read was able to read only first time, and then read was very slow. The read thread was very slow. That the the increment thread actually executed all 5 times, and then the read thread came and displayed something, right? So this is a problem. Again, if you run it one more time, so in this case you see that there are 2 4s but no 5s. I run one more time, I get 2 1s, no 5s, and so on. So every time when you execute, right, here 2 3s, 2 5s, no 2 and 4. So you see, this is basically what we are calling it as a race condition. So race condition meaning that either you are trying to read and write using 2 different threads. So read after write, or write after read, or write after write. Right? Read after write, write after read, or write after write. These 3 conditions will cause the race condition to happen in the global variable. So I could actually change this code, and I could say that instead of printing this value, I could actually put this also here. Counter equal to counter plus 2, let's say, for example. I can put this also. So here we are doing write and write, right? So again, there is a race condition because we are doing write and write. So race condition always happens whenever you have write activity combined with either the read or the write activity from another thread. Okay, if you have 2 reads, then there is no race condition. Okay, so if you just have a printf here and printf here, then there is no race condition. But if you have reading and writing, or reading and writing here, or writing and writing, then you have a race condition. So this is what the problem we have in the threading environment with the global variables. Okay, we need to deal with this, and I'll come to that little bit, in a couple of slides from now. There's one more function, there is one more system call that allows one thread to inform the other thread to cancel out. or basically terminate. So if one thread wants to terminate the other thread, then that thread can actually inform the operating system to terminate the other thread by providing the thread ID. This is similar to sending like a kill signal, right, to another process from one process. Okay. However, there is a difference between the kill and the cancel. The cancel depends on the operating system, and when the operating system is able to send the pthread exit command to that thread. So basically, what happens is, let's say thread 1 wants to terminate thread 2. So the thread 1 will be calling the pthread cancel with the thread 2 ID. Okay. Now the operating system will get this information. So operating system will try to execute the pthread exit command on thread 2. That is how this command works. Okay. So again, this command is not deterministic. Depending on when the operating system gets this message and when it is actually able to execute this pthread exit on that thread 2, it all depends on the scheduling mechanism and the operating system, right? So this is something again non-deterministic, but it can be done. Here is a comparison for the functions between the process and the thread that I have provided. So fork is pthread create, exit is pthread exit, wait PID is pthread join, and so on, right? Get PID is pthread self, and so on. Now I mentioned that there is a there is a issue with sharing the global variables in the threading environment, multiple threading environment. By the way, any questions so far? Is it understandable? So far you are following me through well? Stop in between if you are not able to understand.
Yes, sir.
Okay. So we said that race condition can happen whenever you are trying to access the global variable. So the race condition is even more evident when you actually have your computer execute the assembly instruction. Okay, so when you look at your C program, you may not notice that there is a there is a race condition, but when you look at the assembly code, you will find that there are more race conditions happening than what you actually envision. And I'll show you one example, one simple example here. So let us say that there is a function. In that function, multiple threads are allowed to execute that function. And that function has this simple line of code, x equal to x plus 1. Okay, so this is a simple line of code which is part of the thread function, and multiple threads are actually calling the same function. So multiple threads are allowed to execute the same function, and both the threads can execute x equal to x plus 1. Now, when this instruction is converted into the assembly language, how does it work? So first of all, it has to execute the load operation, right? Because it has to read the data, read the variable x address. So wherever the address of the x variable is in the memory, it has to read the data and load it into the processor registers, right? So it has to execute the load instruction first. Then it will be running the add instruction or increment instruction depending on whatever processor ALU instruction you have, right, by incrementing the register's value. And then it will have to execute the store instruction to store that value of the register back into the memory location. So you have a load, you have add or increment, and then you have a store. So even though your higher level language has x equal to x plus 1, in reality for the assembly language code, it is actually 3 different instructions. Now let us say that that particular instruction is executed by 2 threads simultaneously, because that function can be called by 2 threads simultaneously. If that happens, then what will happen, right? So for example, if you look at this particular code, right, I have 2 different functions actually being called by 2 different threads, but it is not necessary. I can actually say increment count also here, right? So thread 1 can call increment count, and thread 2 can also call increment count. Nobody is telling me that I cannot do this. I can do this. So which means the same function which is incrementing the counter value is being called by two different threads, and therefore both the thread will try to increment the value like this. That is exactly the example that I am showing you, right? Now what will happen? So let us assume that the thread 1 came first and it executed all the three instructions: load, increment, and the store. And then the thread 2 came and then it incremented load, increment, and store. There is no issue, because then the instructions are executed in sequential manner and the final outcome that I get for the value of x is correct, right? So this value of x is correct because load x, which is register, gets 8, then register is incremented, then the x value is updated, then the register is read with the value of 9, incremented, and stored as value of 10. So there is no issue here. But let us assume that the locking mechanism is not there and we are allowed to have both the threads execute concurrently in the interleaved fashion. What is the meaning of interleaving? Meaning that both threads can execute the same incrementation at the same time, right? So let's say that one thread is doing the load instruction, then it incremented the value in the register, but by the time this thread gets a chance to actually execute the store instruction, the second thread started executing that code, this particular code. And so it started loading the value of x from the memory to register. So it also got the value of 8. Then it incremented the value, and now the first thread is doing the store instruction. And then the second thread is doing the store instruction. What is the value? 9. What is expected value? 10. So that means our answer is incorrect. So whenever you interleave or whenever you allow multiple threads to concurrently execute these kind of instructions, right, you end up with the wrong answer, which is not acceptable. Similarly, if you look at this scenario, same thing is happening. We are getting a wrong answer. So what I'm trying to say is this is not allowed, and there has to be some mechanism where we are ensuring that this kind of operation is not allowed by the operating system for multiple threads in the global variables where read write, write read, or write write operations are happening. So how do we achieve that, right? So there are two important concepts that you have to remember. One, critical section concept. What is a critical section? So critical section is a piece of code, right? Is a piece of code which has a race condition or which can cause a race condition, right? So critical section is a piece of code which can cause a race condition, and multiple threads can actually do read write operation or write write operation together, right? So that is what we call critical section code. What do we need to do to solve this problem? We need to apply what is called mutual exclusion. What is the meaning of mutual exclusion? Mutual exclusion means that that activity has to be separated out. So that means that if one thread is executing critical section, the other thread should not be allowed to go through the critical section code. So that means if one thread is executing this command, this line, then the other thread should not be allowed to execute that line. What does it mean? It means that we need to implement the critical section code in the atomic fashion. We need to execute the critical section code in the atomic way. Okay. Now there are several methods which were mentioned in the operating system books or earlier versions of the operating system books, but those solutions were meant where the computer had a single processor. single core. Okay, so if you look at this next few slides, right, these next few slides are meant to have the solution for a computer with a single processor. However, in today's computer, we don't have a single processor. So in the multi-core environment, none of these techniques which are mentioned is going to be working. Okay, and why that will not work, I'll just explain to you with an example now. Right, so first let us look at how the architecture of current system is. I think some of you may have studied that during the or you may have studied during the computer organization course, right? So here we have the core or a processor, right? Here you have the control unit or ALU, or basically all the execution units. You have data path with registers. So these are the local CPU registers. Then you have the local cache, L1 cache. Right, so this is your L1 cache. This is your L2 cache. So L2 cache is shared between multiple cores. I'm not shown it here, but generally in today's modern computer systems, we also have one more cache level, which is the third level cache, L3 cache. Right, so you have L1 cache, you have L2 cache, you have L3 cache, and then you have the main memory, and then you have the disk storage, right? And why this architecture was created? So that we can access the data fast. Your L1 cache is much faster compared to your second level, third level, and especially the memory, right? So as you go down the level here, right, from main memory to L2 to L3 to L2 to L1, L1 is the fastest cache, then L2 cache, and so on, right? So this architecture allows us to get the data as quickly as possible. But this also creates a problem for us. And what is the problem? That is what we are going to study next. So let us assume that this, in this diagram, I'm only considering one level cache. Okay, so you can imagine that even with one level cache, if this is the problem, then with multiple level cache, the problem will become multifold, right? So you have the private cache here for each of the processors or cores, and then you have the main memory, and then you have this system bus which is connecting the caches to the memory. Now let's say that P1 has read the value of U variable from the main memory and placed it in the local cache. Similarly, core P3 has read the value of U variable and placed it in the local cache. Now P3 core has done some calculation, and it has to update the value of U. Right? Now it has updated the value of U in its local cache. But then what happens to the value here? What happens to the value here? And what happens if P2 wants to read the value of U? Right? So the problem is that if P3 has already updated the value of U equal to 7, and let's say P1 has read the value of U, but then it is doing some calculation using the U's value, and it is using the wrong value now, because it is saying that the U is equal to 5, but in reality U is equal to 7 according to core 3. And now if P2 is trying to read the value, it is obviously going to read the value from the main memory, which is also incorrect. So there could be these multiple scenarios where the other cores can use wrong value of U variable, while one core has updated the value in its private cache. And this problem is what is known as cache coherency problem. Did you study this in the computer organization course?
We have studied cache, but not this problem.
Okay, all right. So I'm glad I'm sharing something new to you. So this is basically what is known as cache coherency problem. Okay. So the problem is, how do we ensure that the cache values, the local cache values of the variables are coherent in nature, right? Because you can't allow to have different cores using different values of the same variable, right? So that is a problem. So how does the current computer system achieves this? What is the solution? So the first solution is that whenever the processor or core P3 is updating the value of U variable, it will make an atomic update to cache as well as the memory. When I say atomic, what does it mean? It means that no one else, no other cores will be allowed to read or write the value of U until the updates to the local cache and the memory happens. But then the question is, how is that done? How is that done? So to do that, there are two things that has to be done. The first is the system bus will have to be locked for the other cores. So what does it mean? See, this is the system bus, right, through which the data is read and written, right? So in case if P1 wants to update the value or read the value of U variable from the main memory, it has to use this common bus, which is called system bus, right? Similarly, P2 will also have to use the system bus. So when P3 updates the variable in the local cache, it will actually lock the system bus for the other processors. So it will say that the other processor will not be able to read the value or write the value of U variable using the same system bus. So that is the first thing. Second thing, it will inform the other cores that it has updated the value of U variable, and therefore the other core needs to make the local copy, the private copy of the variable as dirty. So which means that the P1 will be informed by the P3 core that you need to make your local copy of U as dirty. So obviously P3 doesn't know that which of the cores has the local copy. So again, it will be a broadcasted message to all the cores, and whichever core has that particular variable in its local cache, it will make that entry dirty. What does it mean by dirty? It means that it is no longer allowed to use that value for any other calculation. And in case if some partial calculation has been done in core P1, it will have to be discarded. It will have to be thrown away. Okay, so this is what P3 has to do to ensure that no other core is using the older value of the U variable. Now the question is that this is done using some messages from the core to core, right? So a processor will broadcast a message on to the other core saying that you make your local copy dirty, fine. But then how do we do the locking of the system bus? So what happens is that in the modern computer system, there is a special instruction that is provided, the special assembly instruction that is provided, which will be called a lock instruction. And lock instruction is added in front of a normal ALU instruction whenever we need to lock a system bus during that operation. So let me show you an example of that one. So what will happen is that whenever we need to execute an operation which is atomic in nature, there are special instructions provided to us. And so I'll go to this C code, right? So this is our own C code, right? And what we have done is this is just the simple function that we have written. Now in this function, we want to use this variable test, which is supposed to be used as an atomic operation, right? For the atomic operation. So what will happen is that instead of using test equal to 2, we will be actually calling this special function atomic set, right? And similarly, instead of using test equal to test plus 2, we will be calling this special function. Why that is? Because what this allows us to do, it allows us to call internally, the operating system will be calling this locking mechanism. So whenever we are calling the add, atomic add function, it will be basically ensuring that the incremented, the addition happens in the atomic way by calling the locking function of the operating system. Okay, so this is basically the operating system code, the kernel code, which actually does the locking for us. But what I want to show you is that this locking is shown in a C code. I want to show you that there is a special instruction that is added in assembly language code, which actually shows you that it is going to lock the system bus. So what we are going to do is that we are going to compile this code and create the object file, and then that object file we are going to convert it back into the assembly code, which we have done earlier. Okay, which we have done earlier. So in order to compile that code, this is the make file that I have provided. This make file will compile the code into object file, and then once the object file is created, we are going to use the assembly code for that. But there is something special that we have to do for this one. We are including the kernel, we are using the kernel header files. Okay, whenever you use the kernel header files, those header files are the special header files that are provided to us, and I'll show you that. If you go to user source Linux headers, I think I'm using 5.13.0 generic. Okay, so if you look at this folder, there will be include folder in that. And there will be various header files over here. And these header files we have to use when we are compiling this particular special code, right? So whenever we are using this kind of headers, we have to compile it, or we have to use the make file like this. And if we get a chance to actually, towards the end of the semester, if we talk about device drivers or creating our own system calls, then I'll be talking more in detail about this particular make file. But for now, just assume that this is the make file that we have, and we need to use this make file to create the object file, right? Now, this make file actually use the kernel build directory. You can see that there is a kernel directory, and we are putting that kernel directory as this. So we cannot actually compile this code in the Windows file system. We cannot compile this code in the Windows file system. We have to compile this code in the Linux file system. So what I have done, in the home folder, I have copied the test atomic.c, right? So that file is here, okay, and even the make file is here. Test atomic make file, right? So the make file is here. So what we will do is we will copy that make file as a make file, and then we will run a make. Now I may have to run clean because I had already executed it once. So I need to run using clean. So it will create a new object file. Now you can see that it creates the object file, but then it creates one more type of object file, which is called .ko file. .ko stands for the kernel object. So whenever your object file belongs to the kernel, right, kernel source, whenever you are including a kernel source header files, then it also creates this .ko file. And we need actually this .ko file to convert it into the assembly language. which then we will do using the obj dump command, which we had seen earlier. Right, so I'm going to basically execute this obj dump command and convert that .ko file into the assembly code. Okay, and now we look at that assembly code. So this is the assembly code from our .ko file, the kernel object file. Now when you go down here, you will see that there is a atomic add function that is called, and the equivalent assembly language is here. So you can see what is added, right? So normally we see only add L, right? So we are just adding two numbers, but when we are adding these two numbers, it is adding this lock instruction in the front. So this lock instruction is basically telling the other cores to lock this system bus. So while this add instruction is being executed, the system bus will be locked, and no other processor will be allowed to do anything on the system bus. This is how that cache coherency problem is solved. Any questions?
No,
Are
sir.
you able to gather what I'm saying?
Yes, sir.
Okay. So the the computer architecture. See, this is why I'm trying to show you all this. Maybe this is very low level stuff, but the important thing here that you have to understand is that design of the computer system has effect everywhere, right? Because this is the computer system which is going to be running your software, it's going to be running your operating system, it's going to be running your compiler. So whoever is making changes to the processor architecture, right, they have to worry about all this supporting system, right? So the operating system has to take an advantage of the new features that are implemented. The compiler, GCC compiler, has to be updated to take an advantage of this new, architecture, right, and things like that. So obviously, it is the GCC compiler who is converting that code, right? It is the compiler is the conversion is taking the assembly code and converting, or rather taking the C code and converting into assembly. So it has to know, right, that it has to include this locked instruction whenever there is an atomic addition or atomic subtraction or whatever it is, right? So this area is very, very important, and computer architecture, the the software writers who write the compilers, who write the operating system, will have to work very closely together to make sure that they are able to take an advantage of all the features which are there on the system. Any questions from today's lecture? So let me stop here. It's 9:45. Let me stop here. We will cover the more locking mechanism in the next lecture, and I hope to see you guys in the LT from Monday, right? So Monday at 12 o'clock we'll be covering the lecture in the LT. So please be there. I am looking forward to see you guys all. Any questions from today's lecture or anything? Okay. If not, thanks everyone.